The next talk we have is Jean-Pierre Williams from UCLA, and we'll be talking about dating young impact craters on the moon. Jean-Pierre, whenever you're ready, we are ready for you.
I'm just looking for the share my web camera.
That's going to be in the upper left corner, Jean-Pierre.
Okay, great. All right, thank you. So yeah, I'm going to talk about young impact craters on the moon, and specifically focusing on dating them using these small craters that are superposed on their continuous ejecta blanket. So just as an overview here, quickly, I'm going to sort of generate my own crater count isochrons independently using the observed annual flux of small objects colliding with the moon, so I can compare those with existing isochrons. And specifically, I want to focus on how different target properties can influence the results, and also talk a bit about secondary craters. And I'm going to specifically focus on 3 craters where we have exposure ages from Apollo, North Ray, South Ray, and Cone Crater, and then change gears and talk about Giordano Bruno, one of the far side young craters that we heard a bit about this morning. So just as a brief overview, which I don't need to spend too much time here on this, but you know, the exposure ages are correlated with crater populations, which then allow us to anchor a chronology model from which we then generate these crater retention age isochrons, which I'm showing the Neukom et al. Model here on the left, or on the right, sorry. And basically these are the expected or predicted size frequency distributions for a given surface age. And so what I'm going to do then is basically generate my own versions of these using the power law fit to satellite data in the Brown et al. 2002. So here we've got a power law distribution of the cumulative number of objects colliding with the Earth as a function of energy. And if we make some assumptions about average density and encounter velocities, we can convert those to diameters and then scale those that population of impactors to the moon and generate size frequency distribution of craters. And this is a similar approach that was taken by Ivanov in 2006, short paper there. And I think it's, with all the great LROC data now, it's worth sort of revisiting this approach and kind of reassessing it. So I then take these modeled production functions and put them into this tool called CraterStats, provided by Mikkel and Newman in 2010. And that provides an easy way to look at crater counts and compare them with these modeled isochrons. So I then, oh, I lost part of my slide, didn't translate here, I apologize. Basically, there's an equation here that's missing, so I'll just quick describe it. Basically, the crater scaling here I'm using is referred to as the pi scaling, where the transient crater volume can be related to these 2 non-dimensional numbers, one which tells you something about the importance of the gravity scaling, and one about the strength scaling. And so the first non-dimensional number, which you can't see here, but you can see the words, is the lithostatic pressure at the depth of excavation ratioed with the dynamic pressure during impact. And then the strength scaling term is the characteristic yield strength of your target material ratioed with the dynamic pressure during impact. And so these are inversely related to your resulting crater volume. So if you increase the yield strength of your impact material, you get a smaller resulting crater. And conversely, on the gravity scaling, if you're on a planet with a higher gravity, you get a resulting smaller volume for a given impact. The lithostatic pressure, which is the target density times gravity times some characteristic depth, which is taken here to be the radius of the impactor. So since this is dependent on the impactor size, the smaller the impact, the less important gravity scaling becomes, and you reach a point where the strength scaling begins to dominate. And so, as you would predict, that smaller sizes, the target material properties become more important. So here's some representative materials taken from, this is whole sample 93, going from dry sand down to hard rock, sort of increasing strength of material. So this Y bar values here in this column are your target material strengths, which play an important role. The target density plays a small role as well. And then these two parameters, the K sub 1 and the mu, are empirically fit parameters. The K1 is a scaling factor, and the mu is an exponent factor that's related to the efficiency of your target material at dissipating energy and is related to porosity. So the more porous target materials have a lower value. The two rock materials here have a higher value. And so I basically use these materials to generate some model isochrons, which I'm showing over here on the right. And so I have the Neuquem isochron is the black line, and then basically going from the dry sand down to the hard rock along the table, going from right to left. So you can see as you go to stronger target materials, you get a larger deviation from the Neuquem isochron. And so the Neuquem isochron kind of lies somewhere similar to dry sand, but I'm also adding an extra one in here, which is lunar regolith, where I just set the strength to 0, sort of a cohesionless version of the lunar regolith. And that in the dry sand sort of bracket the Neuquem et al. Isochrons. So I then did some crater counts just to compare with these different modeled isochrons. And I'm not going to talk about Tycho, but I looked at North Ray cone and South Ray, which we have samples, cosmic ray exposure ages derived from Apollo samples. And so we've got North Ray at about 50 million years, cone at about 25 million years, South Ray at about 2 million years. And then there's this little crater. Here's South Ray down here, and Baby Ray, which is then superposed on the ejecta. So we know that's less than 2 million years. So these are generally used as tie points for calibrating the crater counts. So I did some small areas around these craters on the continuous ejecta just to compare with previous results in these isochron models. And so here's an example on the left of one of the models. This is showing South Ray and Baby Ray using, and here I'm just showing the regolith isochron where I assumed it has no strength, and I actually get a really nice fit of the 2 million years for the South Ray. And that would then put Baby Ray at less than 1 million. The right-hand figure then is a summary of all my counts showing basically the cosmic ray exposure ages on the x-axis, and then my crater retention ages on the y-axis for the various isochron models. And so if I get it matched, then they would follow along this black line. And then you can see I've included the Neuquem et al. Isochrons. And so you can see here in the black, these points sort of straddle that black line, which is no surprise because the Neuquem isochrons were meant to fit these cosmic ray exposure ages. And then you can see that I've then in the blue, red, and the cyan colors, I then have the dry sand, the regolith with no strength, and then the regolith. So sort of increasing strength in the isochron models from the target material. And so my dry sand and sort of cohesionless regolith model sort of straddle the Neuquem et al. Values and this black line. So there's sort of two ways to maybe interpret this plot. One is that if we assume all these craters are primary craters and that the flux of projectiles that I'm assuming are representative of the last 50 million years, then that would mean that we can maybe start to put some constraints on the target material at the sort of characteristic depth that's being excavated by these small craters that I'm looking at. On the other hand, if we assume that the nominal regolith properties are really probably what we should be expecting, the fact that that model is consistently giving me older ages may in fact imply that there are a lot of secondaries in these craters. And these would be probably self-secondaries where you've got blocks of material being launched at high angles that then fall back to the surface to form craters instantaneously on the ejecta blanket. And so you can kind of think of my model as sort of a forward model in that I have to, if there are secondaries present, then since I'm only producing primary craters, I then have to run my model longer to match the crater density. So keeping that in mind now, I'm going to shift gears to Giordano Bruno, which is a crater we heard a bit about this morning. I'm showing the new diviner-derived rock abundance map here on the right, superposed on LRock NAC mosaic. And this was also talked a bit about by Becky Gent yesterday. She showed this is one of the highest rock abundance ejectives of any crater. And this scales from blue at 0 up to the red, which is exceeding 30% rock abundance. And so you can see that it has a very heterogeneous distribution of rock abundances around it. So we can sort of anticipate that the material properties, the target material properties around here are not going to be homogeneous. And there's a talk this morning by Deepak showing also that the mineralogy also is very heterogeneous around this crater as well. So we can kind of zoom in and take a little closer look at one of these areas that has a very high rock abundance. And you can see here up in this red area where we're at around 30% rock abundance, it's dominated by these very large tens of meter scale blocks. And these areas tend to be almost devoid of impact craters, whereas if you go down below here where you have a lower rock abundance, you suddenly see an accumulation of craters. And so both these regions are presumably getting hit by the exact same amount of projectiles. But because you've got these large blocks that are much larger scale than the projectiles, all that energy is probably going into fragmenting and fracturing these blocks rather than creating impact craters. So this kind of tells us something that there's already kind of a hint here that there's probably a heterogeneous distribution of crater populations that maybe is somewhat correlated with rock abundances. So anyways, I did some counts on the west side to try and avoid some of these high rock abundance areas and blocks, just to compare with other estimates. So here's the Moriota et al. Results using Kaguya, and they get results that fall somewhere between 1 and 10 million years. And that's pretty consistent with what I'm getting. Using the Neuquén model, I'm getting about 7 million years. And then left of that, I have the dry sand and then the sort of cohesionless lunar regolith. And they're all sort of between 1 and 10 million years, which is fairly consistent. Fleischer et al. Pointed out, though, that they sort of attribute this discrepancy or variation in crater ages that they see as possibly being a result of self-secondaries. So I'm going to show one more example real quickly here of where I also see a discrepancy in crater counts. And so I'm going to focus here on this melt deposit here that's on the ejecta blanket. This is right here where this white arrow is. And so if we do counts on the melt deposit up here, and then we do some counts down here, we can compare them, and in fact get quite different results. So the blue here is now the age I get for the impact melt deposit, which is less than 1 million years, as opposed to off the impact melt where I get around 10 million years. So if we then assume that that melt deposit is hard rock, which it does seem to be, all the impacts on the surface seem to be throwing out blocks of material rather than a granular fluidized ejecta. So it probably is a hard rock target material. And we use that model. The isochron then, which I'm showing here on the right, then gives us a very close match of about 9 million years. So the different target materials, I think, goes a long way in explaining this. However, I think there is something to this story of secondaries in that there's some examples here where we see what appear to be pre-existing craters that have now been buried by this impact melt. And here's one example on the left where the impact melt, there seems to be a ring structure that looks like a pre-existing crater that was then buried when this deposit was in place. And we can find a couple of other examples where there's craters off the impact melt that also appear to have some melt deposits within them, implying that these were pre-existing craters that were in place prior to the deposition of this impact melt. So to summarize, I've been able to, using only fairly small craters in limited areas, am able to get consistent ages with the Neuquén production function. But my model production functions sort of demonstrate how small craters can be very sensitive to the target properties. And then also scaling the craters using a nominal regolith properties, I sort of consistently get older surface ages, which may indicate that there are secondary craters present there. So the fact that the crater populations around Giordano Bruno ejecta are highly variable, I think is due both to secondary craters and also lateral variations in target properties, which may correlate with diviner rock abundance values. And with that, I'll stop.
Great, fantastic, thank you. So Catherine Niche is typing in the presenter question window, but until then, actually I was very intrigued by the end of your presentation there, well, the whole thing, of course, but at the end you were talking about looking at the differences between impact melt and just off the impact melt. What are your plans for looking at other areas across the moon at other craters with large-scale impact melt, and correlating between those and looking at the isochrons there? Are you planning on expanding the work? Yeah. Sorry, go ahead.
Oh, yeah, sure. No, I think definitely it's worth trying to find other examples of this to really kind of see how important this really is and how much of the maybe the variations we see on these ejected blankets really is attributable to differences in target properties. Right. But I think the point here is that if you're going to use these small craters, they are sensitive, so it's a possible source of error in these estimations.
Yep, absolutely. Catherine Niche writes in, could the high rock abundance areas actually be younger, i.e. due to recent landslides?
They do. They seem to be correlated with a lot of the rays coming out of Giordano Bruno, so I think they're related to where rays are preferentially ejecting large blocks of material. And if you notice on the impact melt deposit, that's actually not a region of the highest melt, highest rock abundance value. So they seem to be correlated with where there's large blocks that have been ejected out, and you can sort of see that's where a lot of the rays coming out of Giordano Bruno originate from. So I think I don't know if they're related to landslides. I don't think so.
Okay. Great. There are a few other comments, but if you could please just read through those, and if any